It's science, but not as you know it. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with me, Chris Smith, and also with a very special guest. He doesn't manage to make it on the show so much these days because he's very busy at the moment, but he has kindly agreed to come back for this one-off special show, and that's Phil Rosenberg. Hi, Phil.
Hi, Chris.
Good to have you with us. Now, coming up this week, we'll be seeing a supernova from start to finish. We'll be hearing how scientists have watched the complete sequence of a star blowing itself to pieces. Also, how scientists have found a new body clock inside our brains, and get this, it wakes us up for mealtimes. And also the new material that can repair itself if it gets damaged. That's all on the way. Phil.
Thanks, Chris. We're really looking out into outer space this week because later today the Phoenix mission is set to touch down on Mars and look for water and also the hallmarks for life that could once have flourished there. We never know. We'll be talking with one of the scientists behind that mission.
And we'll also be finding out how scientists have been recreating the conditions of distant planets in their laboratories so that they can put probes through their paces and make sure they're going to work when they get where they're going. And we'll also be hearing from a scientist who's discovered where the meteorite that wiped out the dinosaurs came from.
And also on the way, we'll be getting to the bottom of how we could communicate with extraterrestrials, although there might be a few technical issues.
The basic problem with communicating with aliens is that the nearest stars are 3 to 10 light years away. So if you said hello, it would take 3 years for that message to get to the alien star and 3 years to come back.
So it could be a pretty strange conversation.
It certainly could. Thank you, Phil. But right now, if you've got a space science question for us, you want to talk about Mars, for instance, then do get in touch. You can email us, chris@thenakedscientist.com.
The Naked Scientists Podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
We certainly had an explosive week in the world of science this week, Phil, with scientists actually being able to see a star ending its life.
Absolutely, and this is the first time we've basically been able to see the process from start to finish of a star basically blowing itself up. This is what happens when a star comes to the end of its life. It basically just destroys itself. And Princeton researcher Alicia Soderberg and her colleagues were actually lucky to spot this basically by chance. On January the 9th this year, they were using a satellite called SWIFT to look at a galaxy 88 million light years away.
That's not close, is it?
It's pretty far away. It'd take you a long while in your car to get there. And suddenly, in the same galaxy, a bright flash of X-rays they saw. Nothing that they expected from this galaxy. And it lasted for about 10 minutes. And essentially, just by chance, they'd spotted a supernova going off, this star blowing itself up. So they managed to feed the coordinates of this supernova to other telescopes around the globe, including the Hubble Space Telescope. And quickly, everyone looked at it and managed to watch what happened as this supernova processed through its different stages.
Why did they see the X-rays? What do we think's going on to make that happen?
OK, well, what happens when a star ends its life, a big star like this, is the insides basically start to collapse. And as the insides collapse, they form a massive shockwave, and then the whole thing bounces back and explodes. And in the very hot area around this shockwave, as it blows itself outwards, you get X-rays formed, just simply because there's such intense heat going on. And so, yeah, this is the first time we've ever been able to see this sort of process all the way through.
What, presumably because by the time people spot it and get all the big telescopes onto it, most of it's already happened. So
yeah,
because they happened to be looking in just the right direction at the time to see it, they then had everything pointing in the right direction almost instantly.
Absolutely. I mean, the whole process lasts maybe 10 minutes or so. And, this is a star that's been there for probably 10 billion years, minding its own business, and suddenly in 10 minutes, the whole process ends. So to happen to catch that on pure chance, is a million to one shot, essentially. So it's just good fortune that we managed to spot it this time.
And the key question, Phil, did the observations agree with what the theoretical scientists think should happen when a star ends its life?
So that's quite difficult. Actually, we've, up until recently, not really known how on earth a supernova happens. When people try to create a computer model of what happens during a supernova, what they tend to find is that the whole thing doesn't work. They actually can't make a computer model of a star explode. So actually being able to see this for the first time really helps with that. And these are really important things within the whole universe. Essentially, a supernova blasts material into the universe that is only formed within stars. This is things like iron and lead, gold, all these sort of elements that make up, well, the planets, and us in theory as well. The carbon that we're made of came out of a supernova once.
Yeah, it's amazing to think that we're all literally made of bits of dead star,
Absolutely.
Which all happen to just conglomerate in the right place to make our solar system about 4.5 billion years ago.
Exactly right.
Well, back on Earth for just a second, and everyone says that food's the most important thing in most people's lives, and no exception here, because there's a wonderful piece of research published in the journal Science this week, two researchers at Harvard, that's Patrick Fuller and Clifford Saper, and they've been looking at mice which have had a gene removed from their body clock. Now, the body clock is a cluster of nerve cells that sit in the part of the brain called the hypothalamus, right in the centre of your brain, and this almost works like a genetic domino effect. So a gene turns on, and it trips on another gene, and that trips on another gene, and the whole thing goes around in a sort of molecular domino effect, taking 24 hours to do it. If you remove one of those genetic cogs from that body clock, then the mice can't keep time, because normally, you feel tired at night time and you go to sleep and you wake up in the morning, for example. These mice are in a state of perpetual jet lag. They don't know when to go to sleep and they don't know when to wake up. So one interesting thing with rodents, and probably us as well to a certain extent, is that they can be trained when they're hungry to wake up for food. So if you got used to being fed at 3 o'clock in the morning, despite the fact that you should normally be asleep at 3 o'clock in the morning, you could still override your natural instinct to sleep and wake yourself up at the right time. But these mice wouldn't do that. So the research
all the way through, do they?
That's right. So the researchers thought, what would happen if we put the gene we've taken away back into this body clock part of the brain and see what happens? Will it restore the ability to wake up in the middle of the night to food? And they used a virus to put this gene back in, which the gene's actually called BMAL1. It's just one of these body clock genes. And when they put it back in, the mice stopped being in a perpetual state of jet lag, and they would go to sleep and wake up at the right times, but they couldn't learn to wake up for meal times.
Even if they were fed at midnight every night, they still couldn't wake up.
They couldn't associate that, yeah. So they then reasoned there must be another body clock which is specific for this behaviour, and they put the gene back into another adjacent bit of the brain called the dorsomedial hypothalamus, and this is just another cluster of nerve cells, and then the mice could do it. So it looks like you have a sort of secondary body clock specifically for waking you up and preparing you to eat, which is quite intriguing to think is how we learn when our meal times are going to be.
Absolutely, because I guess you can never quite tell when the next meal's coming, can you, sometimes? OK, back up to space now again, and we're talking about the Mars rovers that are already up there on Mars' surface that NASA put down there in 2004.
It's amazing, isn't it? They put them there in 2004 with the anticipation they were going to last 3 months.
Yeah, absolutely.
4 years later,
and they're still going strong. Yeah, absolutely. It's really a feat of engineering that these things are working still. But actually, they're not working perfectly. And Spirit, one of these rovers, has had a broken wheel for quite a while now. Basically, it's dragging it along behind it as it's rolling along across the surface. One wheel is dragging, and actually, this has been great for some serendipitous discoveries. Essentially, as it's been dragging it along, it's been creating a trench behind it, and
so the wheel is just jammed, and it's literally just excavating a trench, is it?
Exactly. It's just basically dragging a little hole behind it as it's going along. And in this week's Science journal, Cornell researcher Stephen Squires and his colleagues have actually described how this has excavated a small area that has actually what they've found as silicate material underneath. So this is bright white material underneath what we normally see as Mars' sort of red surface. Now in Earth, where we find this sort of material, is actually normally like around hot vents, places that are teeming with life. And also, actually, the silica is really good at preserving fossils and the characteristics of this life after it's dead. So this could be a really useful place to go look in the future for actually finding possible evidence for past life on Mars.
So what they're saying is that this environment where the rover has scraped up this trench and shown these silicates, that must have been a sort of hydrothermal vent system or something in Mars' early life.
So something like that, you're looking at hot water and basically salt coming out of that water to create this silicate material.
And because that's a home for life on Earth, using the same sort of model,
extrapolating that across, it could be a potential where there was life on Mars
in the early days, and so that's a good place to look.
Absolutely, that's one of the key locations now.
Thank you, Phil. Now, one of the problems with flying places, including places like Mars, if you want to go there in a space rocket, or even here on Earth if you're in an aeroplane, is that once you're airborne, wherever you're going, if you get damage to your aircraft or spacecraft, it's very difficult, if not impossible, to repair the structure if something goes wrong. But now scientists at Bristol University, and this is a piece of research led by Dr. Ian Bond, have come up with a material that can automatically put things right. And Ian's with us to talk about it. Hello, Ian. Thank you for joining us. How does this actually work?
Well, we've been developing over a period of years now composite materials that have an ability to self-heal. We have small vessels inside the structure with a liquid inside them, and upon a damage event, these rupture and bleed out the liquid to effect some kind of healing function within the structure.
What are the chemicals you're using to do it?
We've been concentrating primarily on using standard sort of two-part epoxy systems, which are the mainstay of the aerospace industry. But there's obvious improvements that could be made to those because they're pretty much off-the-shelf systems at the moment.
So the way it would work is you would have one chemical in one type of tube, one in another, and where the damage is, the two chemicals are blended together and they react.
That's exactly how it works. So you do need both of them to be present. And I guess one of the challenges at the moment is somehow making that reaction or that mixture less sensitive to the particular mix ratios, for instance, so that you can have quite a robust healing process that's not dependent on a certain amount of one or the other being there.
How much of this stuff do you need, and what are the applications for this immediately here on the ground?
Well, we're looking to address the very subtle damage in a structure. So if there's a hole in the structure, for instance, we'd like to think that somebody may notice that beforehand, but it's the dings and bangs and the wear and tear. So it's the small cracks that begin in the structure which are difficult to detect, which we're hoping to address.
So this would be aeroplanes, cars even?
It could be used in cars, yeah. I guess safety-critical structures are probably what we're aiming at primarily. I guess in a car, if it breaks, you can generally pull over to the side of the road, but in an aeroplane, you don't have that option. And certainly in space, you definitely don't have the option.
And how much weight does this add? Because in the aerospace industry, of course, weight is everything. Does this make a plane weigh twice as much and therefore is not going to be useful?
Well, the idea here is, although we may be adding some weight, you can use lighter weight structures because the present design is such that you allow for damage from day one. So you have to have a heavier weight structure than you otherwise would have to cope with the fact that you're sort of fighting with one hand behind your back, as it were, and you're assuming there's damage there. So if you could somehow build in an ability to recover some of that damage by healing, you could potentially have a lighter weight structure overall.
And with the current missions to Mars on the agenda for the next 30 years or so, and the fact that space rockets get hit by things like micrometeors quite often, could this system work in space?
It could do. We've done some previous work looking at this. There's a lot of challenges. The temperature is an issue, the low vacuum, the extreme high velocity of the impact events from things like micrometeoroid. I guess it's the inner structure you might want to protect where they're perhaps not as exposed to the external environment, but you want to maintain structural integrity on, say, a liner where you have a manned vehicle. So I wouldn't necessarily advocate we'd use this on an external structure that's going to be hit by micrometeorites, but it could be used in some form, perhaps in an inner structure within that.
Ian, thanks very much.
That's okay, thank you very much.
It was Bristol University's Ian Bond who's invented a system so that structures can repair themselves in mid-air, if it comes to it, if they get damaged. Don't you think it's amazing, or a stroke of fate, Phil, that he's called Ian Bond and he works on adhesives and polymers?
Yes.
There is this school of thought that says that some people go into certain careers based on what their names are. I don't know if it's true, but it certainly isn't his case.
Laying the facts bare, The Naked Scientists.
It's The Naked Scientists with Chris Smith and Phil Rosenberg.
And still to come, we're speaking to Susan Conway to find out if the valleys on the surface of Mars are evidence of ancient rivers or just simply the result of years of erosion. But first, Ben and Dave want you to drop everything and join in with this week's Kitchen Science.
Hello and welcome to Kitchen Science. This week, Dave Ansell and I have come to Sir John Law's School in Harpenden, and I've met up with Stephen, hi.
Hi there.
And with Daniel, hi.
Hello, good afternoon.
Dave, have you got an experiment lined up for us?
We've got an interesting experiment on how things fall.
How things fall. Are we going to be dropping our volunteers today?
Possibly not the volunteers, but we have a small test subject here, which we are going to drop, indeed.
What do we need to set this one up?
We've got a small plastic cup, one of the ones you have coffee machines, or you could use the bottom of a lemonade bottle, something like that. A pair of scissors and some water.
This sounds fairly simple, so how do we actually set it up?
Well, the first thing you want to do is cut a small hole in the bottom of the glass, one which your finger could fit over the top of. So, Stephen, if you'd like to do that.
Just in here?
Yeah, just in the bottom.
And how big does the hole need to be, Dave?
You've got to be able to cover it comfortably with your finger or a thumb.
So about a centimetre in diameter?
Depending on the size of your fingers, yeah.
How are you doing with the scissors there?
Yeah, it's not too bad. They're not the greatest, but yeah, still.
So, while we get the hole cut in the bottom of the cup, what will we need to do next?
Well, then what you want to do is fill the glass up with water. You're going to have to be quite careful doing this, otherwise the water's going to fall out the bottom. So make sure you've got a finger over the hole while you fill it with water. Then hold the glass with one finger underneath the hole, your other hand stabilising it at the top. Then we're going to drop it by just moving the bottom hand out the way and see what happens.
OK, so, Daniel, would you mind taking the cup, now that we have the hole in the bottom, and filling it up with water? We just provided some water here, so keep your finger over the bottom. And how's that doing? It's quite full. Is it leaking out of the bottom?
Don't think so, no.
That means the hole must be exactly the right size. So Daniel's going to take his finger off the bottom and drop the cup. What do you expect will happen?
That the cup's going to fall.
OK, and Daniel, do you think the water will stay in the cup, or do you think it will come out?
I think it'll come out the top rather than through the hole.
Well, feel free to try this out at home. You'll need a plastic or polystyrene cup, cut a small hole in the bottom, fill the cup with water and put your finger to stop it, and then very carefully drop the cup, pulling your finger off the bottom as you go, and let us know what happens. We'll come back to you later on in the show to let you know.
So what do you think will happen? If you're not sure, just give it a go. Just get a disposable cup, cut a hole in the bottom and plug the hole with your finger. Then fill the cup with water and let it go. Have a look as it falls and see if the water's coming out the top, the bottom, or just not all. Email us, chris@thenakedscientist.com.
Stripping down science.
Okay, let's do it.
The Naked Scientists.
You're listening to The Naked Scientists with Chris Smith and Phil Rosenberg. Now, Phil, we've got a call here from Brian in Harlow who said, manned voyages to Mars, if it takes 4.5 years to get to Mars and 4.5 years back, he thinks it would be impossible for someone to spend 9 years aboard a spaceship. What do you think?
I think he's been a bit pessimistic there. I think it takes a little bit less time than 4.5 years to get to Mars.
How long realistically would it take, do you think?
You'd probably look at somewhere around 6 months or so, depending on exactly the orbits and the trajectories that you're looking at and how close Mars is to Earth at the time. The way it's normally done is that every 2 years, roughly, Mars does a close swing past of Earth, and so that's when we launch all our space missions, every 2 years. So what you're looking at for a human mission is you either go there and back really quickly while Mars is close, or you go there, spend 2 years on Mars until the next close pass, and then come back again. So one of those two options would be the one we go for.
One of the worries with human health isn't just the microgravity and that making our bones thin, it's the radiation exposure though, isn't it?
Yeah, absolutely. And radiation on Mars is going to be a serious problem because it doesn't have, the atmosphere that the Earth does and the magnetic field that the Earth does to protect us like we are on Earth.
So it's not just the space journey, it's also on Mars itself. We're going to have to think very carefully about how we shield our astronauts then.
Absolutely.
Thank you, Phil. Now, coming up later on The Naked Scientists, how scientists are recreating a miniature version of Mars here on Earth so that they can test their space probes and see how spacecraft are going to fare when they arrive on these distant planets. But first, we know that the NASA Phoenix mission touches down shortly, but what will be the conditions on Mars waiting to greet it? Well, Susan Conway is from the Open University. She's studying the processes that have helped to shape the surface of Mars over about the last 4.5 billion years. Hello, Susan.
Hello there.
Thank you for joining us. So what does Mars actually look like if you were to go and stand there? Because we have actually got pictures from it, haven't we?
We have, that's right. Well, where the Mars Phoenix lander is going to land is up near the North Pole. It's getting on for about late spring there, so if someone was on the spaceship and they touched down, they'd obviously need a pretty good spacesuit because the atmosphere's quite thin. It'd be pretty cold. And what they'd see when they got there, probably quite a bit of white frost. This is not water. This would be CO2, carbon dioxide. And they'd be looking about them. You might see the odd black rock. You might see some reddish sand as well in amongst the bits of frost.
Why is it so red, Mars?
It's the iron content of the material. So the dust is actually quite high in iron, and as you know, when you expose iron, to the atmosphere, it forms rust. So that's the red colour. It's basically a rusty planet.
And the sky, because we're used to the sky on Earth being a nice blue colour during the day, obviously.
That's right. Yes.
What do you see on Mars?
Well, it depends on the atmospheric conditions. So on a really bad day, completely black, you wouldn't be able to see anything at all. You wouldn't be able to see your hand in front of your face.
Why not?
Well, the winds on Mars create these huge dust storms, and they kick up all this dust, and basically, just like fog, just like being in fog, but instead of it being water, it's all this really fine red dust, so you wouldn't be able to see your hand in front of your face.
Do we know what drives those dust storms? Because you were saying that the atmosphere is very thin, so
that's right.
If you've got virtually no atmosphere, how do you get such strong winds?
Well, the temperatures on Mars, because of such a thin atmosphere, the temperatures on Mars, there's a huge difference. So to compensate for the thin atmosphere, you've got these huge temperature differences. So we're talking, minus 60 up to 25 degrees in very different hemispheres of Mars, and that drives these extremely strong winds that pick up this really fine dust, making these huge dust storms.
Now, one of the interesting things that when the 2003 Mars Express mission from the European Space Agency got to the Red Planet, it started to give us these amazing pictures of the surface of the planet. There are gullies, there are ridges. It's the most extraordinary sort of surface scape, isn't it?
It is amazing, yeah. I mean, not only the Mars Express, but we've got the MRO, the Mars Reconnaissance Orbiter, is sending back images of 25 centimetres per pixel. So you'd be able to see the studio, you'd be able to see, if you had a car on Mars, you'd be able to see a car on Mars, that kind of resolution. And this is bringing back amazing pictures of some weird landscapes that you just wouldn't expect. Big dunes, gullies that look like they've been formed by water, just some really amazing stuff.
And it's also home to the biggest volcano in the whole solar system, isn't it? Olympus Mons.
Olympus Mons, that's right, yeah. Absolutely massive.
But those gullies that you mentioned,
yeah,
the thing that they look really tantalising because they look like they've been carved by water, because if you compare them to what we have on Earth, say the Grand Canyon or something, although they're a much bigger scale, they do look very similar, don't they? So is it water?
Well, yeah, that's up for debate. There are kind of two features we're looking at. There's a huge feature, as you can see, that's the Grand Canyon, the sort of Valles Marineris kind of feature, the massive one you can see on Mars, and that's thought to have been carved by water a really long time back in Mars's history, so we're talking 2.5 billion years ago.
Well, that is a long time ago, but I thought some of these things looked a bit more recent than that.
That's right, these are smaller features, so a couple of kilometres long, and you can only see them in the most high-resolution images. And they're sinuous, they've got no craters on at all, which shows that they're really recent. And they look just like gullies that you'd find in a ploughed field that's just got water washed over it, or on the Badlands. So if you imagine a desert scenario and you've got the gullies formed in a Badlands, it kind of looks like that.
If it's not water today, what else could do that then?
Well, there's a couple of other theories. Scientists think that maybe it could be dry mass wasting. Dry mass wasting, that's where material just breaks off and falls down a slope in response to gravity. Now, people have difficulty with that because the morphology is not quite the same, the shape is not quite right, but that could be due to the different sediment properties and different gravity on Mars. It could be some kind of CO2, so maybe a CO2 avalanche that picks up material and takes it down slope, or maybe a CO2 explosion. So suddenly the CO2 gets heated up, and then that explodes like something like a volcano, and picks up loads of stuff and tumbles downhill because it's denser than the atmosphere on Mars.
Are you doing experiments here on Earth to model how that would occur, so that you can then match up what you find in the laboratory with the pictures we've got to see if you can match up which of these explanations it's best likely to be?
Yeah, well, we're doing experiments in a Mars chamber that has the same atmospheric pressure and the same temperature. And we're running water downhill there to test the water hypothesis, see if water could actually be stable, because obviously it's outside the stability field for water. It's too cold, too little pressure for water, to see if water can stay active and mobile long enough to form these features. So we're testing that hypothesis.
And what's your gut feeling at the moment?
Well, I think it's water personally, but, it's all up for debate. We'll have to see how the research goes.
If it is water, looking at the terrain, when do you think water last ran then on Mars, conservatively, if it is water?
Well, it could be anything in the last 100,000 years.
Which is very recent, isn't it?
It is very recent, yeah.
Which means if there was life there at some point, it could still have been viable up until 100,000 years ago, which is a blink of an eye, really, isn't it?
Yeah, and if the water formed these features and then has gone back into the ground, and we still have water, liquid water beneath the ground, the little microbes could be still living there in the rock, eating the water, and still sitting there waiting for us to discover them.
Well, let's hope so. Thank you very much.
That's okay.
That's Susan Conway from the Open University. She's with us. If you'd like to ask her any questions, email chris@thenakedscientist.com. Quick question for you, Phil, here from Derek. He's calling from Broomfield and says, if the light we see from the sun is 8 minutes old, what about the gravitational field? Does gravity move at the same speed as light?
There was actually a recent experiment to look at just this sort of thing, or recent observations, and basically, yes, we think that gravity forms at exactly the same, or travels at exactly the same speed as light. And actually, if you plucked the sun out of its orbit, just removed it completely, we would still orbit around the sun for 8 minutes before suddenly the Earth realised that it wasn't there anymore and disappeared off into space.
And a wonderful statistic I heard from Brian Fulton, who's Professor of Astrophysics at York, is that the light emerging from the sun, because the sun's so big and massive and has so much gravity, the light is already something like 1 million years old. So even if the sun went out tomorrow, we'd still have 1 million years more light trapped inside it.
One photon emitted in the middle of the sun takes millions of years to actually travel its way out of the sun because it's such high density.
Thanks, Phil. Quick question for you, Susan, which has come in from Edsel Heinkel, who is listening in Second Life, and says, would a compass work on Mars?
No, it would not. Unfortunately, Mars does not have a magnetic field anymore. The magnetic field on Earth is generated by the core rotating inside the Earth, and Mars has just cooled down too much, and that whole process has been frozen.
So it's lost its magnetic field.
It has, yes.
Thank you very much. Phil?
So Susan and other scientists are helping us understand exactly what conditions are like on the surface of Mars. But if you actually want to send a space probe and explore there, or indeed any planet in the solar system, then you need to know what your probe's capable of surviving and what the conditions are going to be like when you get there. So here's how scientists do that with Mira Senthilingam. Sorry, go on, Chris, you're going to save me now, aren't you?
With Mira Senthilingam.
Thank you very much.
This week, I've come down to the labs of the Planetary and Space Sciences Research Institute at the Open University in Milton Keynes. But it's not your average kind of lab, as there isn't a white bench or a white coat in sight. There are large metal vessels all over the room, really, with circular windows, basically looking like mini spaceships all over the place. I'm here with Martin Towner, who's a research fellow here at the Open University, and he's going to tell me what these vessels are really here for.
Yes, these chambers all get used to simulate conditions on other planets in the solar system. This particular area is mainly to do with the testing and building of instruments. So we have a whole bunch of different chambers to simulate the different environments that spacecraft have to go through on their way to get to Mars or to get to Titan and to land and survive for a period of time. The majority of our work is simulating the Mars conditions for upcoming future missions.
What is the environment like on Mars?
Mars is very different from the Earth. The atmosphere is a lot thinner than Earth's and is also CO2, carbon dioxide, rather than oxygen and nitrogen like we have here. It's also a lot colder. A nice sunny day on the equator on Mars might get up to just above freezing, whereas a cold winter night time you might be talking minus 120 degrees centigrade. The sunlight is also very different. Mars is further from the Earth, so the light is a bit dimmer, but it's also a lot harsher because there's no ozone layer around Mars, so you have a stronger UV ultraviolet on the surface. On Earth, the burn time on a bad day is, half an hour, whereas on Mars you're talking a couple of minutes. It'd probably be the least of your worries if you were on the surface, but the ultraviolet is so strong that it effectively sterilises the surface of the planet.
But how do you know that these are definitely the conditions?
Well, in most of the cases, they've actually been measured. There have been spacecraft that have landed on Mars. They've measured the temperature, the wind speed, the air pressure, so we actually have data for that. There are big climate models in the same way that people do climate modelling on the Earth. People do climate models for Mars as well, so the global conditions are understood. Things like the ultraviolet flux is less well known, but can be modelled because you know the composition of the atmosphere, you know how far away from the sun you are, so you can work out all these things.
We've got all these chambers here in which you try to recreate these conditions, so how do you go about doing that?
Well, because of the low pressure on Mars, you have to have a big metal chamber that you can take the air out of and then fill it with the Mars atmosphere. So you have a big pump connected to a big metal chamber, and this one is about 2 meters long, about 1 meter diameter. Pump all the air out, fill it with a little bit of carbon dioxide, which gives us the atmosphere. We have a bunch of big lamps inside, which can be switched on and off by a computer to give us the day-night cycle, because the Mars day is slightly longer than the Earth day.
What kind of lamps?
Ultraviolet lamps, and then also a normal light bulb type lamp, which gives us the visible spectrum as well as the ultraviolet, because we need both. Temperature is done using liquid nitrogen through a big copper plate. The liquid nitrogen will get us down to below minus 150, which covers the worst case on Mars, and then we control that to bring it up and down to do the day-night cycle or to simulate different areas of Mars, equator, North Pole, South Pole, things like that.
Do you put all of these conditions in one go in each chamber, or do you look at different things in each chamber?
No, the chambers tend to be specialised. I mean, for people studying astrobiology like life on Mars, they want a small, nice, clean chamber. They may not be interested in the light, they might just want it cold and dark because they're studying things that are underground. Whereas if someone is doing more physical processes like wind and sand blowing around, they may want a great big chamber so that the air has got space to move, but they might not be too interested in getting the absolute coldest temperatures because things like wind-blown sand is not really dependent on whether it's minus 20 or minus 50.
But why is it important? What kind of effects do these conditions have on the instruments in the first place for you to have to study this so much?
Mainly it's the temperature, especially when it gets very cold at night and then a little bit warmer during the day. You repeat this day after day after day, and it just starts to have wear and tear on the instrument, on the joints, on the soldering and the electronic components in the instruments, and also things like the battery as well. You also have to be very careful with the lighting. Things like plastics and stuff tend to degrade under strong ultraviolet conditions.
So how do you overcome this?
It's the old adage of test, test and test again, basically. I mean, you have to pick the right materials so that they don't crack or fade or bend or just creep slowly under these conditions. This also affects the accuracy of the instruments as well, which you have to measure so that somebody will know that their instrument works equally well at minus 60 as it does at minus 20 in the middle of the day or in the middle of the night as well. So you just have to work your way through all the different combinations of instruments and environment conditions and then weed out anything that doesn't make the grade and replace it maybe with a better material or a better design.
Survival of the fittest.
Yes, basically.
Is there nowhere on Earth that you could maybe go to try and get these conditions naturally?
There are some places that are close. The Antarctic dry valleys are the one that people traditionally use. It's very cold, very dry. Because of the conditions, you get a strong ultraviolet from the sun, but you don't get the right atmosphere. You know, you're still trapped in the Earth's atmosphere. And at a practical level, doing fieldwork to Antarctica and taking all your instruments out there is actually a lot more expensive than just building a chamber in the lab and testing them there.
And there was me thinking, Phil, that Cambridge was quite a harsh environment as well. I don't need to build a posh lab facility. That was Martin Towner, by the way, from the Open University. He was explaining to Mira Senthilingam how he puts probes through their paces on distant planets, but without having to actually leave the lab.
And still to come, we'll be finding out more about the Phoenix mission itself and what we hope to learn from it. Also, how a chance collision in the asteroid belt that lies just beyond Mars produces a meteor that actually probably did it for the dinosaurs, so 65 million years ago.
Thanks very much, Phil. If you'd like to join in the show, you can email chris@thenakedscientists.com.
The Naked Scientists. Brought to you by thenakedscientists.com.
It is The Naked Scientists with Chris Smith and with Phil Rosenberg. And we also beam this programme live into Second Life. Now, that's at 6 p.m. UK time, if you're not in the UK, which, confusingly enough, is 10 o'clock in the morning, Second Life time, because Second Life is based in California, so we work to their time. So if you want to find us in Second Life, then go to Second Life, go to the Scilands continent, and look up The Naked Scientist, and you'll see we've got a beautiful, very nice mansion there. And if you drop in on a Sunday, 6 p.m. UK time, 10 o'clock in the morning, Second Life time, you will see other listeners who are tuning into the programme, like some of the people who have already sent in questions, and you can meet them, or at least their avatar. Speaking of which, Phil, we have heard from Wherefore Wybrow, who is in Second Life, says, does the UV exposure make solar panels more effective on Mars?
OK, well, yes, there is a lot more UV on the surface of Mars because we don't have the atmosphere to protect us. However, Mars is actually a lot further away from the sun than the Earth is. So the sunlight in general is a lot dimmer, and solar panels don't just respond to UV, they respond to normal sunlight as well. And Susan, you were saying earlier that there's a lot of dust in the atmosphere of Mars, so that would probably have an effect as well.
That's right, yeah. That's a major problem with the solar panels of the recent rovers, is that they get covered in dust and stop working effectively.
OK, and don't forget about this week's Kitchen Science. You need to get a disposable cup, cut a hole in the bottom and plug the hole with your finger. Fill the cup with water and let it drop. Now watch the cup as it falls and see if the water's coming out the top, the bottom or not at all. Once you've done that, email chris@thenakedscientists.com.
Thank you very much, Phil. Now, it's time to find out what's actually going to be happening on the surface of Mars later today, because the Phoenix lander, which is the latest mission to Mars to explore the surface, is due to be touching down. And William Boynton joins us now from the University of Arizona, where he is in charge of the thermal and evolved gas experiment aboard Phoenix. So, William, the Phoenix mission's just literally hours away from touching down. You must be pretty nervous.
I am. It's been a long wait, and there's not too much we can do about it now, but we're just going to watch and hope everything works well.
So just tell us a bit about Phoenix. What actually is it, first of all?
Well, Phoenix is a lander. It's unlike the rovers that are currently scooting about Mars. This does not have wheels. We're going to land in one location near the North Pole of Mars, and wherever we land, that's where we stay. It does have a robotic arm that can reach out a little bit less than 2 meters in any direction and dig up some dirt and deliver it to my instrument, the thermal evolved gas analyzer, and another instrument that has a microscope and a wet chemistry lab and be analyzing the soils that it digs up.
So what key questions are you looking to answer with Phoenix?
Well, I guess the big key question is we're trying to understand the environment and see if it could have been either now or more likely in the past hospitable for life. The mission is not really a life detection mission such as Viking was a long while ago. this mission is more to understand the conditions and just see if Mars might have been hospitable for life in the past.
Why have you picked the North Pole?
Well, we're there in large part because we found this ice just beneath the surface. This was a discovery made with another instrument I've been involved with, the gamma-ray spectrometer on the Mars Odyssey mission, and we found that the whole North Polar region, northward of about 60 degrees latitude, has very large amounts of ice just buried a centimeter or two beneath the surface. So what we're thinking is this ice might provide a special environment to preserve conditions that perhaps organic molecules might have survived.
What sort of ice is that? Is that water ice?
Yeah, what we're speaking of is water ice, and as I think one of your earlier guests mentioned, when we land, we might see a little bit of CO2 frost on the surface. During the wintertime on Mars, it gets cold enough that the atmosphere, which is almost pure CO2, will condense out on the surface, and we can have in the order of a meter thick layer of CO2 frost on covering all of the ground. But the ice I'm talking about here is regular water ice that would be beneath the surface, and there's a lot of it. It's, as best we can tell, somewhere in the order of 75 to 80% ice and maybe only 20% dirt.
And so what season is it at the moment on Mars?
Right now it's springtime. The ground is warming up. The CO2 frost is leaving. It's possible when we get there all of the CO2 frost will be gone. We might still see some, like in the shadow regions behind rocks, things like that, but it is warming up.
And when you say warming up, relatively speaking, that's still pretty cold, isn't it?
It's still very cold, that's right. We expect the temperatures to be about minus 40 or something like that, perhaps in the middle of the day getting warmer.
And how long will the mission last? How long will Phoenix be able to tolerate those conditions to do experiments?
Well, we expect the hardware itself could actually survive maybe about 6 months. So far, the mission is only scheduled to go for 3 months, and if everything is working well, we're hopeful that NASA will come up with some extra money that we can go for another 3 months. But the craft is solar-powered, and since we're near the North Pole, once the winter starts to set in, we lose our sunshine, and so there's no longer any power for the lander itself.
So just to finish off, could you tell us, William, what's actually going to happen today, and what are the steps as Phoenix comes in to land on Mars?
It's actually a pretty involved process, but what happens is it enters the top of the atmosphere, and it has a heat shield very much like the one the Apollo capsules had, or something, same idea as what the space shuttle has when it re-enters, but essentially something that can get very hot and use friction to slow the spacecraft down a large fraction of the speed. Then what happens is they get rid of that heat shield, and they deploy a parachute, which slows it down still more. Now, because Mars' atmosphere is very thin, as one of your earlier guests pointed out, the parachute doesn't do too well in terms of slowing us down, but it will still slow us down. And then the final bit we do with retro rockets. This is kind of the old-fashioned way of doing it compared to what was done more recently with the airbags surrounding things.
But that was Beagle 2, and it didn't go so well, did it? As in, we don't know what happened to Beagle 2.
No, that's true, we don't. It was also the same technology used on the Mir rovers, though, which did survive, and I guess Pathfinder as well. But the problem is when they get to be, when the landers get to be very big, the airbags get to be very big, and it gets more difficult. So we're going back to the technology that we used on the Viking mission, and are very hopeful that this will set us down very gently.
Well, thank you very much for joining us, William. I hope that you'll be willing to join us in a few months' time when it's all gone well, we hope, fingers crossed, and you'll have some data for us.
I'd be very happy to do that.
Thank you very much. That's William Boynton from Arizona University, who is eagerly awaiting the touchdown of his Phoenix mission to Mars. Phil.
Still to come, Ben and Dave return with the results of this week's Kitchen Science. But first, we need to travel even further than the Phoenix mission, past Mars and out to the asteroid belt, which lies somewhere between Mars and Jupiter. Now, occasionally, objects in the asteroid belt collide and break apart, Often they just create clouds of dust and rock and they just stay within the belt. But sometimes the collisions result in some parts of an asteroid breaking free from the belt completely and possibly ending up on a collision course with Earth. Now, according to our next guest, Bill Botke from Southwest Research Institute in Colorado, that's exactly what happened to bring about the demise of our dinosaurs.
Hello, Bill. Thank you for joining us on The Naked Scientist. So, can you just tell us, where did this asteroid come from in the first place?
Well, one of the interesting mysteries that we've had in the field of asteroid impacts and such is what kind of body produced the impact that killed the dinosaurs about 65 million years ago. And in the process of doing a completely unrelated project, we came across evidence for a very large asteroid breakup that happened in the asteroid belt, between the asteroid belts located between the orbits of Mars and Jupiter. This breakup event was about a 170-kilometer asteroid, and we believe using different techniques we know its age, that it broke up about 160 million years ago. But interestingly enough, the fragments from this breakup event took a long time to get out of the asteroid belt into the inner solar system, and we think there's a pretty strong chance that one of these fragments was actually sort of the killer bullet that brought about the end of the dinosaurs 65 million years ago.
What were those asteroids doing there next door to Mars anyway?
Well, the asteroid belt itself, we believe, is sort of the leftover remnants of the original building blocks which formed the planets. At one point, when the planets were forming in the inner solar system, we had a lot of objects that looked like asteroids. We had bigger objects that ultimately became moon-size and Mars-size, and ultimately we built the planets like Mercury and Venus and the Earth. But there were some leftovers, and these leftovers were caught in this somewhat stable region between Mars and Jupiter. And so the asteroid belts, in a sense, are our ancestors. They tell us what the original building blocks look like.
And how did they jostle together in such a way that one of them ended up on a collision course with Earth so recently, 68 million years ago, in a solar system that's over 4.5 billion years old is really recent?
It indeed is. Well, something maybe some of your listeners have probably don't know, but it's interesting to think about, is that why do we even have asteroids hitting the Earth? Why should this take place? Because if you place a lot of asteroids on orbits close to the Earth and such, eventually the Earth will clear them away and there'll be nothing left. Well, it turns out that the asteroid belt has mechanisms take place inside it, which actually, in certain interesting ways, can cause small asteroids to move out of the asteroid belt and onto orbits where they can cross the orbits of planets. And this has to do from a combination of effects. There's actually, interestingly enough, a player in this game is how sunlight affects asteroids, and another player in this game is how the tiny gravitational kicks produced by Jupiter and Mars can actually move asteroids from the asteroid belt into the inner solar system.
So I guess the really big question, though, Bill, is are there any more loitering out there that could do for us the same way as it did catastrophically for the dinosaurs?
Oh, certainly. Right now, there's probably on the order of about 1,000 asteroids larger than 1 kilometer in diameter or so that either on Earth or can cross Earth's orbit or they can come very close to the Earth. Now, fortunately, we've had astronomers from around the world searching for these asteroids, and we've actually found, we believe, a good fraction of all the big ones. So we probably have found maybe about 70-80% of these kilometer-sized asteroids. None of them, fortunately enough, are on an orbit or a trajectory which is going to take them into the Earth in the near future. But there are some others out there that we're still looking for, and there's some smaller guys that perhaps don't cause global damage, but could cause regional damage and local damage. And so we're going to continue to look for the next several tens of years until we find all the threatening asteroids.
Bill, thank you very much, and thank you for that reassurance that you're still out there looking for them.
Thank you very much.
That's Bill Botke, and he's a researcher at the Southwest Research Institute in Boulder, Colorado, explaining how two rocks about 300 million kilometres away could nonetheless wreak havoc here on Earth when they arrived later. Phil.
Now it's time to go to Diana O'Carroll for this week's Question of the Week.
Hello and welcome to Question of the Week from The Naked Scientist with me, Diana O'Carroll. This week we're looking for something out of this world.
Hello, I'm Jesus Zafra from Nerja, Spain, and this is my question. Knowing the possibility of life somewhere in a star like our Sun, do we have any possibility of communication with our nearest stars? What kind of device should be used? Thank you very much. Bye.
How are we going to communicate with other species in our galaxy when there are such massive distances involved?
Hi there, my name is Dr. Richard McMahon. I'm a reader in observational astronomy at the Institute of Astronomy at the University of Cambridge. Because light travels at a fixed speed, it takes a long time for a signal to reach us. The basic problem with communicating with aliens is that the nearest stars are 3 to 10 light years away. So if you said hello, it would take 3 years for that message to get to the alien star and 3 years to come back. The other problem, of course, is aliens will not necessarily have communication in the same kind as us. So what we would have to do is send signals that are numbers, like 2, 4, 6, 8. So that's the content of the communication. The second part is how do we communicate? So scientifically, I think there are two real approaches that are currently available to us on Earth. One is the standard technique, which is to use radio signals, and we listen with the biggest telescopes on the Earth. The Arecibo telescope, which is a 300-meter diameter, has been used. But radio astronomers are currently working on the design of a radio telescope, which will be 10 times larger. Those telescopes will be mainly used to listen for extraterrestrial life. An alternative approach is to use lasers. Lasers have the advantage that they're highly directional. And so you could point a high-powered laser at a specific star. One thing about technology is that we're in a period where technology is improving all the time. And if you want to communicate with aliens and you think it's going to take you many years to start this conversation, it is possibly better to wait maybe 10, 20, 30 years until our technology improves significantly.
You can't send a text or an email to your local solar system just yet, but it looks like lasers and massive telescopes might be the tools of communication for the future. That is, if there's anyone out there listening. For next week's question, you will need to listen to a famous Australian musical instrument.
Hi, this is Nick Lacey from Margaret River, Western Australia. My question of the week is about the acoustics of the didgeridoo. Could you please explain the science behind the cubic capacity of the internal chamber of the didgeridoo in relation to its length?
And after that, I'll be diving into this fishy question.
Hi, my name is Will Jimenez, and I'm calling from San Diego, California in the U.S. My question is based on a previous question of the week where we found out that the concentration of dissolved salts in the ocean is constant. If so, do saltwater fish have a higher permeable skin versus freshwater fish, as they don't have to worry about losing all their electrolytes due to osmosis? If this is the case, how do fish like salmon cope while being able to live parts of their life in both saltwater and freshwater?
If you're a didgeridoo scientist or you know of an alternative way of adding extra salt to your fish and chips, then do tell us about it. Send an email to questionoftheweek@thenakedscientist.com or have a look at Question of the Week on our forum at thenakedscientist.com/forum.
Thank you very much, Diana O'Carroll, who does Question of the Week for us every week. If you've got a question that you think would qualify for Question of the Week, then do please send it to us. Chris@thenakedscientist.com.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
This is The Naked Scientist with Chris Smith and Phil Rosenberg. We're talking about the science of Mars this week, partly because of the Phoenix mission to Mars, which lands this week, and hopefully will tell us a lot more about the surface of Mars. But we've had a number of people who've come in with some very interesting questions for us. And Wherefore Wybrow, who's listening in Second Life, asks you, Susan, how long are the seasons on Mars?
Well, the seasons on Mars are longer than the ones on Earth, due to the fact that Mars's year is longer than Earth's year.
Because it's further from the sun?
That's right, yeah.
It's basically got further to go round.
It's got further to go round, yeah, that's correct. And so Mars's summer is about twice as long as you'd expect on Earth.
Which, if you're having good summers like they do in Australia, would be fantastic. But a bummer if you live in Britain on Mars, isn't it?
Yeah.
twice as long rain, to be honest, yeah.
Right, if you keep your questions coming in. But first of all, it's time to go back to Ben and Dave, who are dropping cups of water in the name of kitchen science.
Welcome back to Kitchen Science. We're still at Sir John Law's School in Harpenden, and I'm still with Stephen and Daniel, who are helping us out with our experiment today. What we've got set up is a plastic cup with a hole in the bottom, and Daniel's holding the cup. It's full of water, but his finger is blocking it up. Are your hands getting wet there at all?
No, not too bad.
Well, Stephen cut our hole, so you obviously did a very good job.
I think I did.
And what we need to do now is to drop the cup. Now, you said earlier that you think the cup will just drop and the water might not come out. Do you still think that's what will happen?
Well, the water may come out, I think.
OK then, Dave, so do you want to count us down?
OK, if you want to hold that nice and high so we can see what happens as it drops, just push down on the top so you're not holding it at all with the top hand, and then just pull the bottom finger away very quickly.
Well, there's a bit of a splash, and my feet didn't get wet, but luckily Stephen was crouching next to me and he could see what happened. So what happened? Did the water come out of the hole in the bottom?
It didn't, actually, so I was correct the first time. So probably shouldn't have changed my mind.
When you dropped it, did you see the water coming out?
Only from the top, when it bounced and hit the floor.
So, although there was a hole in the bottom of the cup, the water didn't actually come out of that hole. Why did this happen, Dave?
Well, start off with try and work out why water falls out the bottom normally. So if you've got a cup of water and you hold on to the cup and you take your finger off the bottom...
Well, the water just came out the bottom of the hole.
It did. It just sort of dribbled onto the floor, Dave, so that's not particularly successful.
That's not particularly exciting, no. But this is because gravity's pulling on everything, but we're holding the cup up, so gravity's pulling on the water and that pulls it past the cup, down through the hole, and so it falls out the bottom. But if you let go of the cup as well as letting go of the hole at the bottom, then everything's going to be pulled towards the earth at the same speed. So the cup and the water are going to fall down at the same speed and not move relative to each other, so the water doesn't come out of the hole.
Oh, fantastic. So because both the water and cup are under the same force of gravity, the water doesn't fall any quicker than the cup does?
Yeah, so it can't fall out the bottom.
OK, so that proves that gravity pulls on everything at the same speed. But what's this got to do with space?
You may have seen pictures of astronauts up in space, and it seems like there's no gravity.
I have, yeah, and you see things like little blobs of water floating about.
Yeah, that's right. If something's in orbit, actually all it's doing is falling. A spacecraft in orbit is just falling all the time, always falling towards the Earth. Because a spacecraft is falling and everything inside it is falling at the same speed. They don't move relative to each other, so it's as if there's no weight.
So is this how the Vomit Comet works, the aeroplane that you can take that gives you a zero-gravity experience?
Yes, exactly the same. The plane just picks a course to fly, which would be the same course as if something had been thrown up in the air and was falling under gravity. So everything inside it is falling under gravity, exactly the same speed as the plane, so they don't move relative to each other, so it's as if there's no weight.
So because the plane is falling at the same speed as everything inside it, you inside feel like you can float around?
Yes.
So have you ever heard of the Vomit Comet?
I have. I actually saw a TV programme on it, but I didn't know it worked like that. I just thought it was quite interesting to see people float around.
And what do you think? Do you think you'd have a go on the Vomit Comet if you were given the chance?
Yeah, I'd definitely like to see what it's like. A new experience, I suppose.
Fantastic. Well, thank you ever so much for joining us. And that's all we have for Kitchen Science this week, and we'll be back with more very soon.
Thank you very much to Ben and Dave, who were doing this week's Kitchen Science, and also thank you very much to Stephen and Daniel from Sir John Law's School in Harpenden, who were helping them out. Now, we've got absolutely acres of questions coming in so far. This is a very interesting one. Zanzibar Rothschild, who's listening to Second Life, says, Susan, what can we find out about our history from an asteroid?
Well, like our previous guest was saying, the asteroid belt is remains of a planet that didn't quite make it. So we can look at those asteroids. If we could get a sample of one, we could look at its structure, and then basically we can explore the Earth's centre, what would be in the Earth's centre, so the core and the mantle and their composition, by looking at these asteroids, because they're bits of...
Because the same sort of planet-building soup that made us, made
exactly.
those asteroids, so they're a kind of vestige of what we're made from, so we can learn a lot about our origins.
Our planet, yeah, that's right.
Phil?
Absolutely, and one of the bonuses is that sometimes we get meteorites fall on Earth, which are essentially just bits of asteroid, and we can analyse those.
We've actually got bits of Mars here on Earth, haven't we?
Yeah, just a few little bits that have come off and been blasted off by asteroid impacts, and just through luck landed here and someone's found them. So.
Fantastic. John in Colchester says, why do we assume that life on Mars is carbon-based, Phil?
Well, I guess essentially we assume that because that's all we know. You know, people have speculated that there could be silicon-based life or other more exotic forms of life, but we've only ever seen carbon-based life, so it's a good place to start, really. Something that's based on carbon and water is probably what we're looking for, and if we're going to look for something more exotic, we're probably going to struggle to find it in the first place, to be honest.
And Christos Quinnell says, how long would it take to terraform Mars, do we think? In other words, turn it into some place that humans could live. What do you think?
It's going to be a long time, isn't it?
It's going to be a long time. Hundreds of... Yeah.
Because thinking about it scientifically, you've got to change the composition of the atmosphere of a whole planet, and you've got to undo the reasons that Mars doesn't have an atmosphere already, which is that it doesn't have a magnetic field, isn't it? Because
that's right,
the solar wind has gone past, there's no magnetic field to deflect it, so it's become desiccated.
That's
Absolutely.
right.
And I mean, even we're still looking at probably 30 to 50 years before we even send a man to Mars, so even before we even think about starting to terraform Mars, it's going to be probably centuries away.
Yeah.
There's an interesting question which is actually more Earth-based, but you're welcome to have a go at this because we were talking about past vestiges of life, and this is that Flynn Morgan, who's actually 5 years old and listening via our website, nakedscientist.com, he says, are there actually dinosaur bones that have turned up on Earth in Britain?
Well, I think I can answer that one. The answer is certainly yes. You can see quite a lot of examples if you go to the Natural History Museum, or if you're local, go to the Sedgwick Museum in Cambridge. In fact, one of the researchers there is digging up plesiosaurs, a swimming reptile closely related to dinosaurs, locally in Ely, if I'm not mistaken.
This is an interesting question from Edsel Heinkel, who says, are there completely unknown elements on Mars? One would think not, because the periodic table of elements, which are the building blocks of existence everywhere, pretty much we think are going to be the same here as on the other side of the universe, aren't they, Phil?
Yeah, basically. I mean, the same laws of physics apply here as apply on Mars and as apply, well, we think, at least everywhere else in the universe. So, yeah, but the same basic elements are, the carbon, silicon, all the basic elements are still there on Mars. But, we do get some different mineralogy, so the way they are fitting together on Mars is often slightly different to the way it works on Earth.
Got a question from Andy, who emailed us to say, is there a magnetic equivalent of a black hole? Because black holes suck in light. Is there the sort of magnetic version of that?
Well, in theory, a black hole can be magnetic, or at least the gas that's swirling around it would be magnetic. The gas becomes charged, and essentially you get an electric current going around the black hole along with all the matter, and you get a magnetic field created there. Whether you get something that actually sucks in magnetic fields may be slightly different. Magnetic field, in theory, is very much related to light, so really a black hole should kind of suck it all in at the same time.
And I shall leave you, as we are running out of time, thank you guys, with this poser from Amy, who says, my mum and dad like to have a drink at the weekend. My dad has a gin and tonic with lemon. My mum has a rum and coke with lime. And I'm wondering why the lime sinks and the lemon floats. We don't know the answer, so if you at home have any clues, then do email me this week, chris@thenakedscientist.com, and we'll try and solve Amy's conundrum for her. Thank you very much to Susan Conway from the Open University, to Bill Boynton and Bill Botke, who are our guests this week, and to our wonderful production team. We have Phil Rosenberg, Mira Sinthalingham, Diana O'Carroll, Tom Simpkins and Ben Valsler. Next week, we are going to do our science Q&A. You just send in the questions and we'll try and answer them for you. Have a great week. See you next time.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.